Okay, so before we do anything else, we need to review orthogonality. And so we'll, because that will be important in dealing with equations, partial differential equations. So usually in 2 dimensions, right, R2, you have 2 vectors. We call them I hat, and j hat. And that's the vector 1, 0, and this is the vector 0, 1. And every vector in the plane, call it AB, can be written as a coefficient A times I hat plus a coefficient B times j hat. We call this W, then we get W equals A hat plus A I hat plus B j hat. And the nice thing about I and j is that they are perpendicular, but we can use lots of other perpendicular sets, orthogonal sets. So suppose we have 2 vectors. V1 to be the vector 1, 1, and V2 to be the vector 1, minus 1. They're linearly independent, and we can verify that V1 and V2 are orthogonal by taking their dot product. 1 minus 1 dot 1, 1 is equal to, you multiply the top row, 1, multiply the bottom row, minus 1, and you add them together, and that gives us 0. So V1 and V2 are perpendicular. So that means now if I have a third vector, which we'll call, again, W, I can rewrite W as a linear combination of V1 and V2 in some way. So W is equal to AV1 plus BV2, and I want to know what are the coefficients A and B. So what we can do is we can use the fact that V1 and V2 are orthogonal to actually get a pretty quick solution to this question. W dot V1, oh, good Lord, equals A dot V1, A times V1 dot V1 plus B times V2 dot V1. So I get an equation that involves the number A, but this I know is 0 because they're orthogonal. So W dot V1 is equal to A times V1 dot V1. And so I can solve for the number A just by calculating these 2 numbers. Likewise, W dot V2 will turn out to be B V2 dot V2. So do an example, but I think I have to add a page real quick. So let me do that. Okay, so let's take an example here. Suppose W is vector 7, 10. And that should be equal to A times our vector V1, which was 1, 1, plus B times our vector 1, minus 1. We want to know what A and B are. So we take the dot product of this entire equation, both sides, with 1, 1, 7, 10 dot 1, 1 equals A 1, 1 dot 1, 1 plus B 1 minus 1 dot 1, 1. And those are dot products. So this becomes 7 times 1 is 1 plus 10 times 1 is 17 equals A 1 dot 1 1 dot 1 dot 1 1 is 2 plus, well, 1 plus minus 1 is 0 plus B times 0. So we get A equals 17 over 2. Likewise, what's B? We take this equation now and we take the dot product with 1 minus 1. We get 710 equals A 1 1. Oops, we want to take the dot product with respect to 1 minus 1. Dot 1 minus 1 plus B 1 minus 1 dot 1 minus 1. And what's that? This becomes 7 minus 10 is minus 3. This is 0 as orthogonal, and plus B 1 plus 1 is 2. So a pretty easy way to find the coefficients A and B. As a little bit of a further example, I mean, this was nice because our vectors v1 and v2 actually span the entire plane, so every vector can be written as a linear combination. But we can also do partial expansions of vectors. So suppose W now is a 4-dimensional vector. We'll call it, let me check my notes real quick. One, minus 1, 1, minus 1. So there's a vector. And we'll take two other vectors, v1 plus v2, not v1 plus v2, but just v1 to be 1, 2, minus 1, 3. And v2 to be the vector 4, 1, 6, 0. So v1 dot v2 is going to be 4 plus 2 minus 6 plus 0 equals 0. So v1 and v2 are perpendicular to each other. v1 is perpendicular. v1 is perpendicular to v2. Good. So what does that tell us about W? Well, W equals AV1 plus BV2 plus a third vector, which we'll call we'll call it V3. Right, and the third vector V3 is going to end up being perpendicular to both V1 and V2. So what's A and B? Right, and these are the coefficients. Well, W dot V1 is AV1 dot V1 plus BV2 dot V1 plus this third vector V3 dot V1. Since V3 is perpendicular, this is 0. This is 0 because we already calculated. So W dot V1 is A times V1 dot V1. And W dot V1 is, where did I write that down? W dot V1 is going to be 1 minus 2, which is minus 1, minus another 1, which is minus 2, minus 3 is minus 6. Equals A V1 dot V1, which is 1 plus 4 plus 1, which is 6 plus 9, 15. So A is minus 6 over 15. W dot V2 now equals AV1 dot V2 plus B V2 dot V2 plus whatever this third vector is, dot V2. But that's perpendicular that's perpendicular. So what do we end up with? We end up with another equation. W dot the vector v2 is equal to the coefficient of W in the direction of v2, which is b, times v2 dot v2. And W dot v2, let's see if we can do this in my head, is 4 minus 1, which is 3, plus 6, so that's 9. And v2 dot v2 is 16 plus 1, which is 17, plus 36, which is 17 and 36 is 53. Oh, 9 over 53. So we've broken down W into 3 parts. The part along A, which is minus 6, the part along V1, which is minus 6 over 15 V1, plus a part along B, which is 9 over 53 V2, plus a third vector V3. And you can actually calculate V3 because you know W, you know V1 and V2, and so you can calculate that out. And so it's a partial decomposition because we don't have, in 4 dimensions, if we only have 2 vectors, that's not an entire basis of the space. So for functions, let's add in another page here. Just so we have enough space. So for functions, we can define a dot product by this notation. Right? This is an inner product instead of a dot product. And we just integrate, multiply the 2 vectors together and integrate them. And this plays the same role as a dot product. And it follows the same rules, right? It follows linearity. That means that K1F plus K2G inner product with H is K1F H plus K2F G H. That it's symmetric. Inner product of F and G is the inner product of G and F. And the inner product of F with itself is greater than 0 unless F equals the 0 function, right? And note also the way we're defining this, because we're just doing real analysis, this is a real number. So what an inner product does is it takes a pair of functions and it turns it into a number, just the same way the dot product takes a pair of vectors and turns it into a number. So we'll let f1 of x equals sine x and f2 of x equal cosine x. And then we can define f1, f2, because that's the integral from, say, 0 to 2 pi would be a good interval to take. Sine x, cosine x, dx, and that equals 0. And so note that this inner product depends on the interval, right? If I had taken this from 0 to 3, for example, these wouldn't be orthogonal. But on the domain 0 to 2 pi, sine and cosine are orthogonal. And so sine and cosine act like perpendicular vectors did in our previous example. If g of x is a function, then g of x will be equal to a sine of x plus b cosine of x plus a third function, which I'll call h of x. And h is going to be orthogonal to both sine and cosine. And so how do you find the coefficients here? So inner product of g of x with sine of x in that parentheses is going to be kind of long, so I'll write it down on the next line. A sorry, A sine x plus B cosine x sine x plus the remainder of it, which will be h of x sine x. So what is this? This is A times sine x. That's 0 because cosine x are orthogonal. This is 0 because h of x and sine x are also orthogonal. And likewise, you can find B. So if we take a particular example, if g of x equals x, then x equals A sine x plus B cosine x plus more stuff. How do you find A? The function x inner product with sine of x will be equal to A inner product of sine x with itself, right? Because these two terms are both 0. And this is the integral from 0 to 2 pi of x sine x dx equals A integral from 0 to 2 pi of sine x multiplied by itself. That gives me that. And the integral of x sine x is minus 2 pi. That will equal A times the integral of sine x, which is just pi. And so that gives me that A equals minus 2. Similarly, you can show that B equals 0. And so you can get that x is equal to minus 2 sine x plus some other function on the interval from 0 to 2 pi, and h of x is perpendicular to sine x. And if you had more functions, you could expand it that way. So this kind of calculation shows up a lot in dealing with ODEs, and so we will just wanted to separate that out and make it its own thing.